Greetings everybody, and in particular to the complex analysis gang out there who've been waiting many months for another one of these uploads. It's been like 6 months, over half a year probably, since my last complex analysis video, which is a little bit outrageous. But we're back at it again here today. We're going to be evaluating the integral from 1 to infinity of dx over x squared of x squared minus 1. This one's a bit funny because we're starting at 1. Usually we like to start at 0 or minus infinity, but this is the integral that we have. If you've seen the thumbnail of this video, you might have a rough idea of what the contour will look like. There's going to be branch cuts everywhere. So yeah, that's something we'll have to investigate. Let's just jump straight into solving this integral. So as always, let's start off by defining for ourselves a new complex function that we'll call f of z, just something to integrate. As usual, just let it be equal to the integrand, but replacing all the x's with a z. So there's no z up there. It should be 1 over z squared of z squared minus 1. Now sometimes I would like to refer it in the form 1 over z, and using difference of two squares on inside of this square we have z minus 1 to the 1/2, and then z plus 1 to the 1/2. Sometimes it's just a bit nicer in that form, as we'll see with some of the integrals we'll evaluate. Okay, so as I mentioned before, we have to investigate the branch cuts. Those are quite important because they're going to determine what type of contours we can use and so on. So branch cuts, that's I guess a step 1. I should have written that. So branch cuts, how do we do this? Well, let's consider our function f of z again. Now if you've seen my dog bone contour videos, you would roughly know what we're going to be doing here. We're going to be decomposing our function f of z into kind of like polar form. The reason being is because depending on what branches we choose, the argument of our function will be discontinuous on certain rays, I guess. So if you take a look at the function that we have, since we're dividing by z, we're going to have a polar 0. So if I draw a rough, I guess, diagram over here, we have a pole, that's 0, that'll mark with an x, and we have z minus 1 and z plus 1. Those are going to give us they're going to be branch points at z equals 1 and z equals minus 1 respectively. So there's a branch point at 1 and a branch point at minus 1 because they're in fractional powers. So what that means, since if we have fractional powers, we're going to have the complex logarithm appearing and so on, there's going to be choices of different branch cuts we can make around these points, and we want to align these branches up in a nice enough way such that it's useful for us to evaluate an integral. As in the case of the dog bone contour, I think it was something like we chose two branches which kind of faced in one direction. I think that was how it worked from memory, and we made it so that it was continuous across where the branches kind of double up, and discontinuous everywhere on this interval. We're not really going to get that complicated with this integral. We're just going to simply align the branch cuts so that one of them is facing along the negative real axis and the other one is facing along the positive real axis. That's, I think, yeah, that is what we had in the thumbnail of this video. The reason for doing that is so we can construct path integrals above and below, let's say the right branch cut, and do a little loop around the branch points like so. And because this integral is nice and symmetric and so on, we can do the same kind of symmetry on the other side. And it turns out that these integrals here along these paths, these four paths, are related to each other in a very nice way, and that's why I called the integral I here. So they're all related to I. So we can kind of solve for our integral if we integrate along these paths. So that's the idea. That's why we want our branch cuts to be oriented in that way. So first of all, to kind of get this, let's let's decompose our function f of z into polar form. First thing first, I'm going to write it out as z to the minus 1, z minus 1 to the minus a half, then z plus 1 to the minus a half. Why do I do this? Well, I'm going to rewrite each factor in base e to get that logarithm so we can choose the different branches. So over e log of the z, and then we have that negative power, so negative there. We also have e to the minus a half log of z minus 1. And if you've watched my other videos, you might realize that I usually use ln instead, but since I've taken like uni maths, real analysis and all that stuff, everyone uses log all the time, so I've just kind of gotten used to using log instead of ln. So yeah, apologies if you like using ln, but I've just gotten used to using log because I do maths in uni now and whatever. But anyways, we also have e to the minus a half log of z plus 1. Okay, and now we have logarithms of complex numbers everywhere. Hopefully you remember how to take logarithms of complex numbers. If not, I'll remind you over here. I've made a video on this as well. If you take the log of a complex number, this is equal to the logarithm of its absolute value. So this is going to be kind of like the real part, and you also have a plus I times the argument of z. Now arg is a multi-valued function, so we will have to restrict our argument. That's the thing with choosing branches and whatnot. So we want this arg here so we can choose different branches. That's the idea. So what I'm going to do now, let's rewrite all of this. I'm going to expand out the logs. So this is e to the minus. We have log of z, then minus I times the arg of z. We also have e, so what we can do as well, we can split the exponentials up using exponential properties, and then we also have e to the minus a half. We still have the logarithm. Now we have absolute value of z minus 1, and we also have the imaginary part, which is I arg of z. So distributing this minus a half in, we're going to get minus a half I times the arg of z minus 1, and splitting up the exponential here as well. And finally, we have e to the minus a half logarithm of z plus 1. There should be absolute values here, so this is the real part. And then we have minus a half I times the argument of z. Okay, now this is looking very messy. There's stuff everywhere. I'm going to try and regroup everything a little bit. Notice we have these exponential factors here, which we can kind of turn it back into similar to what we had initially, because notice e and log cancel for all of those factors. So this first factor leaves us with absolute value of z to the minus 1. This guy is z minus 1 in absolute values to the minus a half. Then the third guy is z plus 1 to the minus a half. So this is what we have, and you can kind of think about this as the modulus of our function. Next we have the arguments as well, so these are the remaining factors over here. Notice they all have base e, so we can have a common, base of e, and they all have i's everywhere, so we can factor out an I. Now what's left, we're going to have minus the arg of z. Next we have minus a half arg, so minus 1/2 times arg of z minus 1, and then we also have a minus a half arg of z. So minus 1/2 times the argument of z, like so. No, that should be z plus 1. Did I write this wrong? Yes, that was wrong. That should be z plus 1. Okay, so basically what we have now is a polar decomposition of our function. Modulus, arguments. Now, what we want to do is we want to select specific branches for each of these argument functions. So we're going to let, for instance, notice over here on the branch around z equals minus 1, which corresponds to arg of z plus 1, we want the branch cut to be along the negative real axis, which means we want minus pi to be less than the arg of z plus 1. So this is corresponding to the points z equals minus 1, and we want this to be less than pi. We also want for this other branch around the branch points z equals 1, we want the branch cut to be on the positive real axis, which means we want 0 to be less than arg of z minus 1, and this to be less than 2 pi. That ensures the branch cut is on the positive real axis. And as for this arg of z, doesn't really matter. You can just take the principal argument if you want to. But yeah, since this arg of z comes from this z, the argument function is continuous everywhere, so it doesn't really matter, but we can write that down anyways. Okay, now what I want to do is to calculate the argument of a function as we approach from above and below on each of these branches. And knowing those values there will become quite important later on when we calculate the integrals along those paths, because there's a little lemma that I'm going to state later that will help us save a bit of time. So yeah, let's try to calculate the argument of a function as we approach above and below on each of those branch cuts. Let's do this as a table. So I've kind of already gotten columns here. I'm going to write one more, which is kind of like the final result, I guess. I'm going to put arg of f at the very end. So we need to calculate the value of arg for each of these different cases here. Then we're going to combine all of them together to get the arg of f. So let's take a look at, let's consider the interval minus infinity to minus 1, but as we approach from above. So if we approach from above, what's going to happen to the arg of z plus 1? Well, z plus 1 is right over here, and if you're centered around this point, notice that your argument is going to approach, well, it's going to approach pi. So this is going to approach pi. Arg of z minus 1, well, z minus 1 is here. If you look to the left-hand side, well, the numbers here, the argument's going to approach pi as well. And yeah, finally here, this guy doesn't really matter, but that also approaches pi. Okay, let's consider the same interval again, minus infinity to minus 1, but approaching from above. So let's center ourselves right over here. If we approach from above, then we're going to approach an argument of minus pi. Hope you guys can see that we're approaching minus pi there. If we're centered around z equals 1, which is the second one, so z equals 1, then what's the argument approaching? Well, the argument of, well, this argument is between 0 and 2 pi, which means we're going to be approaching pi. We can't approach minus pi because that's outside of the interval that we defined. And finally, the arg of z, well, that just approaches, what does it approach? Approaches minus pi. Okay. Okay, so that's the left-hand branch done. Let's do the branch from 1 up to infinity, approaching from above. Arg of z plus 1, let's center ourselves over here. That's going to approach 0. If we center ourselves right over here, that's going to approach 0 if we approach from above. Okay, and arg of z, that just approaches 0. Okay, so from 1 to infinity, but we approach from above. So centering ourselves here again, we are going to approach, if we approach from below, that's going to look like it's approaching 0 again. If we center ourselves here, if we approach from below, we are going to approach 2 pi. And then arg of z, that should approach, yeah, that should just approach 0. Okay, so we calculated all these arguments. Let's calculate the arg of f. So what is the arg of f? How do we calculate that? Well, we just take the minus arg of z, minus a half arg of z minus 1, and then minus a half arg of z plus 1. So let's see what that gives us. We have minus pi here, first of all, minus a half times arg of z minus 1, so that's here, so that's going to be pi. And then minus a half arg of z plus 1, so that's this guy, so that's going to be minus another half pi. So this is going to be equal to minus 2 pi. Let's take a look at the second one. So we have, I'll just go through this quickly. So this is pi minus a half pi, and then a plus a half pi. And that's going to give us, these cancel, so it's going to give us pi. Next up we have, these are all 0, so it's going to be 0. And then finally we have 0 minus a half of this guy, which is minus pi, and then minus a half of this guy, which is 0. So this is just going to be minus pi. Okay, so we know what the argument approaches on both sides of the branch cuts. So let's label these. We'll actually need this picture for later. So this is minus 2 pi. this is pi, this is 0, and this is minus pi. And notice this shows discontinuity because the argument approaches different values mod 2 pi. So on both sides of this branch cut, the argument isn't congruent mod 2 pi. That's why it's discontinuous. If this pi was, say, 2 pi, then everything would be good because we're congruent, but it's not, so that's a discontinuity. Okay, so we are pretty much done with this section now on determining the arguments. So this was quite important because it will hopefully save us a bit of time later on as well. So that is step 1 done. Okay, step 2, let's consider the contour. Now, as I said before, we're going to be using a contour like this. So let me just draw it out again. So we have this kind of picture. So we have branch points at -1 and 1. And we have a pole at 0, a simple pole, and we want our contour to look something like that. So I'll try to draw it out again. So we have our branch cuts over here. Now we want to kind of make this a closed loop so that we can close this pole at 0, so we can evaluate its residue and so on. So what I'm going to do is I'm going to construct these arches above and below. This is not my best contour drawing, but should be okay. Now let's label each of these parts. I'm going to call the upper path gamma 1, and this is going to be gamma 2. I'm going to call this a psi 1, psi 2, omega 1, omega 2, and then let's call this path gamma -1 and gamma 1. So we're going to traverse in the positive direction, which means counterclockwise. So something like this. So on these inner paths here, we're going to go this way, and then this way, and this way as well. Okay, so we want to integrate along this contour, which I'll call C. So let's write out some integrals now. So we have the contour integral over C of f of z dz. First of all, that contour C encloses a pole at 0, which means we can choose the residue theorem. So 2 pi I times the residue at z equals 0 of our function f of z is going to be equal to the contour integral over C of f of z dz. But notice we can decompose this path of C into each of these little mini paths here. So that's going to be the integral over psi 1 plus the integral over psi 2 plus the integral over omega 1 plus the integral over omega 2 plus the integral over our gammas. So we have big gamma 1, big gamma 2, and then little gamma -1, and then little gamma +1. That's a lot of integrals. I don't think I've had 8 integrals before, maybe on the dog bone, but I think this is the most number of integrals we've had to decompose into. So yeah, so this is the idea. We also need a little bit of a lemma, so I'll state the lemma here. So what is the lemma? So I don't think this has a proper name or anything, it's just something I came up with for the purpose of this video. So let's suppose that we have some path, let's call it psi, and I'm going to kind of parameterize it by some epsilon, and this approaches another path psi, which is kind of the limits as epsilon approaches 0. And this path psi, this lies on a branch cut. Then what do we have? Well, if you want to evaluate the integral, or let's take the limit as epsilon approaches 0, over the path psi epsilon of f of z, there's actually a very simple way to calculate this, and I might as well do the proof in the statements as well. All we need to do is decompose this f of z into polar form. So this is the limit as epsilon approaches 0, the integral of psi epsilon, and we have the absolute value of f of z times e to the I arg of f of z dz. Okay, but the thing is, as we take the limit as epsilon approaches 0, this e to the I arg f of z, that's going to become constant everywhere. So if you want a bit of a picture, then let's say this is a branch cut over here, then we have some path a psi, let's say this is psi 1, and then we have a psi half, and then it's psi a quarter, and if you take the limit, it kind of approaches this branch cut, which is psi. Notice that along this branch cut, the value of the arguments will be the same everywhere. So this is basically going to become constant in the limit. So we can write this as the limit as epsilon approaches 0 of e to the I arg f, and I'm going to put a psi there, a psi epsilon there, just to indicate we're approaching on the path psi, of the integral along psi epsilon of f of z dz in absolute values. So this is going to help us out quite a bit with the evaluations of some of these integrals here, because we have paths that we kind of want them to approach zeros. So we're going to make them kind of narrow into that branch cut. So I said this result will help us quite a bit, because we know what the argument of f approaches above and below the branch cuts. So that's the lemma I wanted to state. Let's go on to the next step, which is evaluating the contours. So step 3, integrals. So the first set of integrals I want to do is the integral from integral over sine 1, sine 2, omega 1 and omega 2. So these will be quite nice to evaluate. So let's take the limit as epsilon approaches 0, and these paths, they're also going to approach some radius r. I forgot to mention that. So from minus r to r, and we kind of want to take the limit as r approaches infinity, so it matches with this interval of integration. So we're going to take the limit as epsilon approaches 0 and r approaches infinity. And yeah, you can kind of think about these paths here as being parameterized by epsilon, where epsilon is the distance away from the branch cuts and so on. So you can come up with some parameterization for this, but essentially, if you take the limit on the integral on psi 1, parameterized by epsilon, of f of z dz, then this is going to be equal to, well, using this result here, what we do is we take a look at the argument of a function from above. So from above, we establish that it approaches, this one over here approaches 0. So we have e to the I 0 out the front, and then we have the integral from, now we're going to take the limit as epsilon approaches 0 here, but that essentially just becomes the interval from 1 up to r. We're taking the limit as r approaches infinity as well, so that's going to be 1 to infinity of the absolute value of, let's use a new integration variable t dt. Okay, now notice that on this interval our function will be positive everywhere, so we can just remove those absolute values like so, and this, you may notice that this just becomes I. So e to the I 0 is 1, and this integral is basically, since f of t we defined it as follows, it's basically the I that we started off with, which is quite nice. So that was quite simple. Let's take a look at the integral over psi 2. So taking the limit as epsilon approaches 0, r approaches infinity, integral psi 2 epsilon f of z dz. What is this going to be? Well, we take e to the I arguments from below, so that's going to be e to the minus I pi, and if we multiply by the integral from, now psi 2, it's going in this direction, so that's going to go from r back to 1, or from infinity back to 1. Now we're going to have the absolute value of f of t dt. Now the thing with this one is we want to switch these bounds a little bit, but that's not too tricky to do, because notice e to the I pi is minus 1. We can distribute that minus 1 into this integral. That's going to flip everything, and notice on this interval as well, 1 to infinity, our function is positive everywhere, so we can remove the absolute values, leaving us with the integral from 1 to infinity of, that's going to be f of t dt, but this is just I once again. Now let's take a look at the next one. So limit as epsilon approaches 0, r approaches at infinity, integral omega 1 epsilon of f of z dz. What is this going to be? Well, omega 1, that's this guy over here. From above, the argument approaches minus 2 pi, so this is e to the minus 2 pi I, integral. Now we are going to go from minus r up to minus 1, or minus infinity up to minus 1, if we take the limits. And we also have absolute value of f of t dt. Now the thing with this integral is that our bounds are negative and it's also a bit reversed as well. So on our next equality, we're going to be making a little bit of a substitution. We're going to map t to minus t, so just doing a little bit of a change of variables there. E to the minus 2 pi I, that's just 1. But we're essentially left with the integral infinity to 1, since we put a negative in front of these bounds. Absolute value of f of minus t, since we map t to minus t. And dt, that's going to pick up an extra minus sign, so minus dt. Okay, but notice we can take this minus from this differential and distribute it into the integral to switch the bounds. Also, notice that f is an odd function because we have x squared here and we have x. So if you plug a negative x in, you're going to get the negative of the function. So f of minus t, you just bring that minus out to the front. But since we're inside absolute values here, that doesn't really matter. That leaves us with the integral from 1 to infinity. We switch the bounds here of absolute value of f of t. But on this interval 1 to infinity, f is positive everywhere. We can ignore these absolute values. But this is just I once again. So 3 of our integrals evaluate to I. Surely the fourth one does as well. We can just guess, or we can, well, we should probably check properly. So let's take the limits. Epsilon approaches 0, r approaches infinity. The integral over the next one is omega to epsilon of f of z dz. That's going to be approaching from below, that's e to the I pi. And we also have the integral. Now, omega 2, it's going to go from minus 1 to minus infinity. So minus 1 to minus infinity of absolute value of f of t dt. So again, we're going to map t to minus t. This e to the I pi, that's minus the integrals. The bounds are going to pick up minus sign, so this is 1 to infinity. We have f, as discussed before, we have an f of minus t, but that minus we can bring out and dissolve into the absolute value. And dt, well, we pick up a minus there as well. So this, well, these negatives here are going to cancel. We're going to end up with the integral from 1 to infinity. Absolute values are gone because our function is positive on this interval of f of t dt. And this is, no surprise, once again, I. So in fact, all these integrals up here, they evaluate to I. So we have 4i essentially from these 4 integrals, which is quite nice. So the final 4 we're going to work with these ones, and they actually all evaluate to 0. So what I'm going to do, I'll probably put a timestamp somewhere if you don't want to watch that, because I'll admit it might be a bit boring. So yeah, timestamp will be somewhere for that. But yeah, let's go ahead and do that. We won't need this lemma anymore. That was just for the first 4 integrals. So let's rub all of this out. And let's take a look at the integral over gamma 1. So integral over gamma 1 of f of z dz. Okay, so what we want to do is we want to take an estimation of this integral. So I'll put absolute values on either side of it. And what we want to do is we want to show that this integral is less than or equal to some value that's dependent on r, and show that if we take the limit as r approaches infinity, this is bounded above by 0 essentially, which forces this integral to be 0. So how do we do that? Well, first of all, let's parameterize this a little bit. So we'll notice that I should have kept my contour picture, but the path basically looks like that in the complex plane. Notice we can parameterize our z as being r, let's make it big R, times the e to the I theta, where theta ranges. Now, it does start slightly above the real axis, but because we're taking the limit anyways, we can just start it from 0 and make it go up to pi. And it follows that dz is equal to I, r e to the I theta d theta. Okay, so what is this going to become? This is going to be equal to the absolute value of the integral. Now, we're going to go from 0 to pi. Okay, now f of z, which is this guy, what I'm going to do is I'm going to use this form actually. And I'm going to substitute z for this r e to the I theta. So we're going to have a 1 over r e to the I theta, and then we have r e to the I theta minus 1 to the 1/2, then r e to the I theta to plus 1 to the 1/2, and then we have I times r e to the I theta d theta, and then absolute values. Now the nice thing is these r e to the I thetas will cancel, and now we can use the integral inequality to bring these absolute values on the outside into the integral, because we're integrating with respects to a real variable. So this is less than or equal to integral from 0 to pi, absolute value of everything, but the absolute value of I up there is going to be 1. And we're just going to take the absolute value of everything down here. So this is r e to the I theta minus 1 to the 1/2, and then r e to the I theta plus 1 to the 1/2 d theta. Okay, now we have these guys on the denominator, and usually when we have things with r, we like to use the reverse triangle inequality. I'll remind you of how that works. So reverse triangle inequality, it says that if you have the absolute value of a minus b, this is greater than or equal to the absolute value of the absolute value of a minus the absolute value of b. And this is nice because we have things on the denominator. If we show that the stuff on the denominator is greater than or equal to what we currently have, then we found a new upper bound, essentially. So the first factor, that's obvious. So this is less than or equal to the integral from 0 to pi, 1 over, and then this is our a, and this 1 is our b. So we can directly apply this inequality. So you have the absolute value. What's the absolute value of a? Well, it's the absolute value of r, which is just r because it's positive. Absolute value of e to the I theta is 1. Then we have minus the absolute value of 1, which is just 1. And then we have a half. For the second factor, it's a bit more tricky. It's actually very simple, but basically we just change this plus into a double negative. So we have something minus something, like so. And we do the same thing. So we have absolute value of the first term, which is r, minus the absolute value of minus 1 this time, which is just 1. And this is to a half d theta. And notice both of these, well, they're the same. We can actually get rid of these absolute values because we're taking the limit as r approaches infinity anyway, so it doesn't really matter. But this is going to be equal to, notice the whole integrand as well, that's independent of theta, so it's just a constant, we can pull it out. So it's 1 over, we have r minus 1, combining those two factors together, and then the integral from 0 to pi of d theta, but that's just going to be, it's just going to be pi. So very simple. So what we've shown is that this integral is less than or equal to pi over r minus 1. Okay, which means we can use the squeeze theorem now, because this guy is always greater than 0. So 0 is greater than or equal to the limit as r approaches infinity of the absolute value of the integral over gamma 1. But this guy is less than or equal to the limit of what we found, so limit as r approaches infinity of pi over r minus 1, which is equal to 0. So as you can see, this basically gets squeezed between 0. So yeah, therefore the integral over gamma 1 in the limits as r approaches infinity is going to approach 0. And now you can do the exact same thing for the integral over gamma 2 as well. The only difference is that instead of from 0 to pi, we're going to be going from minus pi to 0. And all the algebra and everything's literally the exact same. It's just the bounds of the integrals are the same, but going to get the exact same upper bounds. So yeah, it's not really worth doing it again. So we've concluded that the integral over gamma 1 goes to 0, and the integral over gamma 2 does so as well. So we've done 2 of these integrals. Let's focus on the last 2 here as well. I think we can just evaluate one of them. The other one's pretty similar anyways. So yeah, let's just clean this up, and we'll take a look at the integral over gamma, little gamma sub minus 1. So I'll draw a little picture of what those integrals look like. So they look like, so this is the real axis. They just go around these branch points here in this fashion. So yeah, something like this. And so this is gamma minus 1 and this is gamma 1. So let's calculate the integral over gamma. Let's go for minus 1 first of f of z. Again, we want to show it's equal to, equal to 0 in the limits. So what I'm going to use is, let's put absolute values everywhere. We're going to approximate these guys once again. So first of all, let's parameterize this. So notice every z on the path minus 1 can be represented as minus 1 plus epsilon e to the I theta. So epsilon e to the I theta, that's just the circle, and was centered about minus 1. Which means dz is going to be equal to I epsilon e to the I theta, d theta, and theta is going to go from minus pi up to pi. Okay, so substituting this in now, we have the absolute value, integral, so this is integral over minus 1, integral from minus pi to pi, f of z, but instead of z, we're going to plug this guy in. So let's use this form of the function again. So we have 1 over z, which is minus 1 plus epsilon e to the I theta. Now we have z minus 1, but that's just going to be epsilon e to the I theta minus 2. Then z plus 1, which cancels with this minus 1, which gives us just epsilon e to the I theta to the 1/2, like so. And dz, that's just going to be I times epsilon e to the I theta d theta. End of absolute value. Now what we can do now is we can cancel, let's say, this factor with this, but this is going to be raised to a half power now. And we can use the integral inequality once again to bring the integrals, or bring the absolute values in. So this is minus pi up to pi. Absolute value of the inside is going to be 1 over, we have minus 1 plus epsilon e to the I theta, and then epsilon e to the I theta minus 2 to the 1/2, and we still have epsilon e to the I theta, but this whole thing raised to the 1/2 power d theta. And we do need absolute values here as well, I just remembered. But notice the absolute value of e to the I theta is just 1, so we can just replace this simply with epsilon to the 1/2 power. But notice, just as before, here this whole thing is a constant, so this whole thing just kind of jumps out in front of the integral, and essentially this, if you take limit as epsilon approaches 0, this is going to approach 1. This is going to approach, that's going to be square root of 2. This is finite. In the top, that's going to approach 0 because we have epsilon to the 1/2. So this clearly approaches 0 as epsilon approaches 0. And it can do a very similar thing for the integral over gamma 1. The only thing that's going to be different is basically these bounds here, I'm pretty sure. But everything else should be the exact same. So this also approaches 0 as epsilon approaches 0, which is quite nice. So that's those integrals done. And we have one more little part to calculate as well, which wouldn't take too long. That's the residue. So what do we have so far? We have these integrals, they contribute 4i to the contour, and these integrals are absolutely useless, they're 0, but they still need to be there. Okay, so the last thing is, I think this is step 4 now, which is the residue at z equals 0. So we have the residue at z equals 0 of f of z. What is that? This is a simple pull because this is z to the first power. So using the formula, it's the limit as z approaches 0 of z minus 0, which is z, times the function, which is 1 over z squared of z squared minus 1. Z's are gone, and in the limit as z approaches 0, we're going to get 1 over the square root of minus 1, but that's just 1 over I, which is equal to minus I. So that's simple. So this residue approaches I, so I guess this whole entire thing here approaches 2 pi I times minus I, but that's just equal to 2 pi. So we have 2 pi now is equal to 4i plus a 0. So I guess step 5 now is the final result. So we have, 4i is equal to 2 pi, which tells us that I must be equal to pi on 2. And I is the integral we started out with at the very start. So pi over 2 is the answer to this integral. Felt like this went for longer than intended. Hopefully it's not too long after I edit it down and everything. But yeah, that's pretty much for this video. I hope you guys enjoyed it. Bit of a nice one with branch cuts and everything. Everything else was just pretty standard contour integration. So I guess it's nothing too spicy. You might have some more spicy integrals coming up later, or if you have any spicy integrals that you want me to calculate, just drop them down in the comments below and I'll have a look at them. But yeah, that's all from me. Hopefully the uploads will become more consistent over the holidays as well, because I have one more uni exam and then I'm free, so uploads should be more consistent. And yeah, also have the topology and manifold series, which is going on as well. I've uploaded like 3 videos for those. Hopefully I get more done on that over the holidays. Just gotta record a bunch of videos and edit them. But yeah, subscribe so you don't miss out on that. Up until the next one, have a wonderful day, and I'll see everyone in the next video. Bye bye.